All right, I've started my recording. So I'm Chandramouli, one of the TA for your CY04 basic thermodynamic course. So basically, this week I'll be dealing with some problems related to Joule's effect, Joule-Thompson effect, then isothermic compression or expansion, and adiabatic compression or expansion. So if you have any doubt, you can stop me at any point during the discussion and ask me. And or if you have some doubt now, you can start. You can ask me, and we can start from there. So Vinita has left the meeting, so I think it's just me. So I'll continue the recording. And if you guys want to if you have some doubts after seeing the video, you can always put it in the NPTEL forum, and I'll be active in that and clear some of your doubts. All right. So now let me get started. I'll share my screen. I'll present. Yeah. Okay. All right. So now I have already started the recording. So I think everything is in place. So what I'll do is I will go to the page and I'll start solving some of the problems that are related to your assignment problems. Since nobody is there, I'm not going to ask any questions, so I'll start solving the problems directly. All right. So now the first question is during Joule's expansion of Van der Waals gas, which of okay, somebody has joined. Okay, Vinita has come back. Yeah, Vinita has come back. All right. Vinita, can you see my screen actually?
Yes, sir.
Okay, okay. Thank you. So, it'll be quite easy for both of us if you're quite interactive. If we can, answer some questions, it'll be easy for us to go through all the questions quite quickly. All right. So now, so basically this week, what Sir taught was mainly on work done for isothermic compression or expansion, then related to heat, Joule's effect, Joule-Thomson effect, and adiabatic work and expansion. So, so the first question is related to the Joule's expansion of a Van der Waals gas. So first, before going to Van der Waals gas, can you tell me what is the Joule's expansion coefficient for an ideal gas? Uh, did you get a chance to go through all the lectures, Vinita?
Yes, sir.
Okay, so for an ideal gas, what is the expansion coefficient? Say for an ideal gas, the Joule's expansion coefficient is okay. It is also dt by dV at a constant internal energy. So basically, what we see in Joule's expansion is it's nice. So the internal energy of the system remains same, and suddenly the gas is allowed to expand into vacuum. So it's basically a free expansion. There's no pressure acting on it. So if there's no pressure acting on it, so basically the work done is zero, right? So now what happens if the internal energy is constant? So as the volume expands, how does the temperature change is what we want to know. For an ideal gas, the Nj is actually zero. So which implies the temperature does not change as the gas expand. Temperature does not change, okay? does not change as gas expands. However, for a real gas, where there are interaction between the gas molecules, we cannot say the same. So, can you tell me the formula for van der Waals gas? The equation of state for van der Waals gas? Vinita? Pressure is equal to, are you there? Sometimes I don't, if people, oh yeah, there. Okay. Are you there? Can you tell me the van der Waals equation of state? Okay, so it is RT by V bar minus B minus A by V bar square, right? So this gives us excluded volume. Excluded volume. Well, this kind of gives the interactions, okay? Traction parameter, we can call it like that. So this A gives us the kind of interaction that is going on between particles. So now I'll skip the derivation. I'll directly come to the final expression. I'll just write the Joule's coefficient, okay? Because sir actually went through the derivation in the class. So you can check that. If you see here, it is minus 1 by CV A by V bar square, okay? Do you remember this? This part, this formula, NJ formula here over here for Van der Waals gas. Okay. Vinita, can you hear me? Or are you able to see the screen also? Okay, she has left the meeting again. So let's continue. Since she is not there, I'll just discuss the problems directly. So now, as you can see here, for most of the gases, A is greater than 0, CV of course is greater than 0, and V bar is of course greater than 0, which means the quantity Nj is going to be less than 0. What this means is, as temperature increases, sorry, as volume, oh, okay, as volume increases, temperature goes the other way, so temperature decreases. So in case of ideal gas, there's no change in temperature, but for but for real gas, temperature decreases. All right. So now we can just, so basically what will happen is the gas will cool down. So that's what we want. So answer B is correct. All right. So now we'll go to the second question, where again it's an easy question actually. So for an ideal gas over here, we want to know the plot of T versus P at constant enthalpy. And actually, this is related to Joule-Thompson effect. So over here you can see that it is basically delta T versus delta P at constant enthalpy, which is basically the Joule-Thompson coefficient, right? So for ideal gas, Joule-Thomson coefficient is going to be again 0, similar to Joule's coefficient. So, which implies that the slope is basically 0. All right. So, which implies the slope, which is basically delta t by delta h, sorry, delta p at h is going to be 0. So, since this is 0, that means if you draw a graph, if you draw a graph of if you draw a graph of t and p, the slope is going to be 0. Since the slope is 0, it's just going to be a straight line. All right, it's going to be a straight line for is the same t for all pressure values. So you put p and then you have the same t. All right. So let's see. We can just quickly draw here. Okay. See here. Let's say I'll take b over here, t over here. Since the slope is 0, it's going to be just a straight line. All right. So here the options are a parabola, rectangular hyperbola, straight line passing through origin with slope 1. All of these are false. So basically, this is the answer. So let's come to the third question. This is quite tricky, and this question is related to Joule-Thomson effect, but then we just need to expand on what was done in the class. So basically, in the class, Sir took a special case of Van der Waals equation where A was considered to be 0 because there are no interactions. However, that is not the case always. So what we'll do is in this session, we'll derive the Joule-Thomson coefficient for a Van der Waals gas where A has a finite value. All right. So what are the things that we need for this? So what we are going to do is I'll introduce all the required things as we go along. So again, we can always start from scratch where H is equal to U plus PV because enthalpy is going to be constant and we want to see what happens. So now first thing is DH. Okay, what we want is DH. So H is a natural variable of P and T. Okay, somebody has come back in. Just need to. Hello, can you hear me? Hello, Binay, can you hear me? She has left the meeting. All right. I think I'll just continue. People are trickling in, then just going out, and I don't know. I don't know what to tell. Probably you guys can, refer to the um, YouTube videos later. Yeah. So I'll go back to this. Okay, it's a natural variable of P and T. So now, therefore, we can write the total differential dH as del H by del T, constant pressure, right? dP plus del H by del. Wait a minute, or rather we can write it a different way. Yeah, what we eventually need for Joule-Thompson's coefficient JT is basically del, something related to del H 1 minus CB del H del H by del P at constant temperature. Constant temperature. So which is basically going to be equal to del T by del P at constant enthalpy. Okay, so now what I'll do is, first and foremost, we'll represent H, dH. Okay. We can write this. We can differentiate with respect to P, right, at constant temperature. Okay. Is equal to del U by del P at constant temperature plus, since this is a two variable thing, we'll have to do P into del V by del P at constant temperature plus V del P by del P at constant temperature, which is basically, this is 1. Okay, now simplifying it, we have dP T plus, yeah, this is del H by del P constant temperature. So that's going to be 1. So now we have P del V by del P T plus 1. Okay. So this is, let's keep this as equation 1. Now we need del U. Okay. So now let's say consider U. You can write the total differential for U, of course. Consider U, V and T, of course, natural variable. So the du is equal to del U by del V, the constant temperature Tt plus del U by del T at constant V and Tt. Alright. So now, as you know, this is equal to Cv, the heat capacity. So now what I'm going to do is, I'm going to differentiate, divide this by we want dP, right? So I'll divide that by dP. Okay. 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 Done. Divide by dP. So what happens is this becomes, we're at constant temperature, of course. So this will remain the same, this term dt divided by t, and then this dt by dp at constant temperature. Oh, sorry. done something wrong. Yeah, yeah. Okay. TV. This is there. Then tell you. So this is CV, right? Tell P constant temperature. Yes. So as you know, this is constant temperature. This term is going to be 0. Sorry, I was mistaken. This is going to be dB to be dt. Let me erase. There was some mistake I did. Yeah. Yes. dV by, sorry, del V by del P, constant temperature, yeah, plus CV del T by del P, constant temperature. Since it's at constant temperature, this term is going to be 0. So del U, so okay, del U by del P by T is therefore equal to del U by del V, constant temperature, del del V by del P, constant temperature. Okay, so this is 2. Okay, now let's substitute 2 in 1. Let's substitute 2, equation 2 in 1. What we will get is, okay, del H by del P, del H by del P at constant temperature is equal to, we have to substitute for the U, right? We have to, since we're substituting for the U, this is the value for that, which is del U by del V at constant temperature, and then del V by del P constant temperature. If we go up, what are the other terms that are still there? Plus P del V by del T plus 1. Plus P del V by del T del V at constant temperature plus, oh, how did it become 1? Was supposed to be V, right? Yeah, 1 into V. Yeah. Plus V. Yeah. So this is what we have. So now for the next substitution, we need this. So let's keep this as, I mean, we can still, I mean, we can substitute this further. Yes. Okay, somebody has joined. Okay. Oh, okay. So now we have, mm, we need this. So I think we can still simplify this further. Del B by del T is equal to del V by del B T. Yes, we have this. And del U by del V T plus B. Yeah, okay, plus B. Let's keep this as equation 3. Now we need all these terms. We need this term, du by dv, dv by dp. So these are the terms that we need. So first and foremost, for now, del v by del p, del u by del v at constant temperature is given by T del P by del T V minus P. Okay, so now we know what P is. Okay, let me create some space over here. Okay, so now let's substitute this. Let's substitute 4. Let's substitute 4 in 3. 4 and 3. So if we do that, del H by del P constant temperature is equal to, okay, just see there, del V by del P constant temperature. This will be T delta P delta del T, sorry, but constant volume minus P plus P plus V. So this is going to get cancelled. So we have something like this. Del H by del P at constant temperature is equal to T del P by del T constant volume, then del V by del P at constant temperature plus V. Now we need to figure out what these are. For that, let's use this what equation. I'll keep this equation 5. Okay. So now we have this. Now we can go to the van der Waals gas, VDW gas, where pressure is equal to RT by V minus B minus A by V bar square. So now we need two differentials. One is with respect to T, another with respect to P. But then since differentiating V with respect to P is not straightforward, we'll first differentiate P with respect to V and then invert it, or reciprocal. We'll take the reciprocal of that. All right. Let me create some more space over here. Okay. Okay. So now first what I'll do is I will differentiate del P by del T at constant volume, right? That's what we need. Yeah, that's what we need. So that is going to be straightforward because it is, R is let's just be left with minus V bar, and since this A by A divided by V bar square is a constant term, that's going to be 0. So now this is fine. So now what we will do next is we'll differentiate delta P del P by del with respect to del V at constant temperature. So then when we do that, it's going to be minus RT V bar minus B. This is straightforward. So so since it's in the denominator, it's going to be minus 2. So minus into minus is going to be plus. So plus 2A by V bar cube. So now this is quite a tricky term. We'll have to, since we need to do reciprocal of this, let's do this. Let's multiply this V bar cube plus 2A V bar minus B divided by V bar cube to V bar minus B. So this is del P by del V. But we need del V by del P, right? So therefore, what I'll just do reciprocal of this. Del V by del P is equal to v bar cube minus vb 2a v minus b minus rt v bar cube. All right. So now we have this term. We have both the required terms. So, okay, this let's keep it as b, and this I'll keep it as a. So now I'll substitute a and b, equation a and b, equation a and b, and equation 5. So now when we substitute that, what we get is we have del h, of course, then del b at constant temperature, of course. Then we have a t term. Then first differential that we get is r by v bar minus b. So that goes here. Then there's another, yes. So this becomes r by v bar minus b. Okay. Next one becomes v bar minus b whole square to v bar cubed divided by 2a v bar minus b square minus rt v bar cube plus v bar. Okay, so now we have here with this, and the square can get cancelled. So if we rearrange the terms, what we will end up getting, it's quite interesting. Let's do this. We will have rt v bar cube into v bar minus b 2a v bar minus b squared minus rt v bar cube plus v. Then we can try to reduce this term further. So what we will have here is rt v bar cube, sorry, we'll multiply this as well, v bar v to the power 4 minus rt v bar cube b. So then we have 2a v bar minus b squared v bar minus rt v to the power 4. So now 2a v bar minus b whole square minus rt v bar cube. So this term and this term will get cancelled. Okay, am I doing it correctly? Let's see. Okay, so now then what happens is it can be further reduced to 2a v bar into v bar minus b whole square whole square. Sorry, it's going to, okay, let me correct it a little bit. V bar minus b minus rt v bar cube into b. To a v bar minus b square minus rt RT V bar Q. So this is something that we're getting. Okay, whatever I got, is it correct? Let me check. Hmm. Let me just check my notes whether whatever I got is correct or not. Yeah, seems to be fine. So now what we can do here is this is delta H by delta P to the power, sorry, delta H by delta P when the temperature is constant. Now what we need is the Joule-Thomson's coefficient, okay? Nu JT, as we know, is 1 minus 1 by Cp into del H by del P, constant temperature. So then if we do this, what I'm going to do is I'll take V common from the numerator, okay? This V bar. So therefore, it will simplify to minus V bar by Cp divided by 2A V bar minus B whole square minus RT V bar squared into B divided, okay, divided by same 2A V bar minus B square minus RT V bar cube. Now this is the Joule-Thomson's coefficient, okay, for a van der Waals gas. For a van der Waals gas. So now I know this kind of looks little complicated. You know, you have B, you have A playing a role, B playing a role. So it seems to be a little complicated. However, we can do certain assumptions and then see how we can address the question. So if I'll go back to the question where A is greater than RTB by 2. So this is the boils temperature. We want to see whether what will happen to the gas, whether it's going to cool down or the temperature is going to increase. It's as simple as that. Okay. So what we'll do is we'll use that assumption. A is, let's, okay, I'll make some space. So what we want to know is, question is basically when A is greater than RT by 2, RTB by 2, let's keep it as RT for now. Okay. RT by 2, what will happen? Cooling or heating. The gas expands. Okay. Or heating. Okay. So now let what I'll do is I'll take let A be equal to RT by 2. That's what I'll do now. And I'll try to simplify this nu JT. So nu JT is going to be equal to minus V bar by Cp. So since this is RT by 2, you can see here RT by 2. Okay. So 2 into RT by 2 V bar minus B whole square minus RT V bar squared by V 2A again V bar squared minus B whole square minus RT V bar cubed. Oh, sorry, I have to make this to RT by 2, right? So 2 into RT by 2. Okay. So now this 2 will get cancelled, and then you have RT common everywhere. So we can just, remove this. We can just cancel that. So we'll be left with minus V bar by Cp V bar minus B whole square minus bar squared B divided by B minus whole squared minus V bar Q. All right. So what I'm going to do is I'm going to assume few things, okay? Just for the sake of simplicity. Since the gas expands to a big volume, let V bar be much greater than B. So since it's like a big expansion, we'll assume this. Then in that case, what would happen is minus V bar by Cp. This term will be equal to, if that's the case, V bar minus B is approximately equal to V bar. So then we'll have V bar squared minus V bar squared by B. Again, V bar squared minus V bar cube. So we can further simplify this. Sorry. Yeah, once we further simplify, okay, yeah, once we further simplify this, we can just cancel all these V bars. It'll be like this. The cube is gone, so we'll be left with minus V bar by Cp 1 minus B by 1 minus V bar. So now one more thing that we need to do is that we know B is a, okay, I'll have to simplify it one more step. Jt is equal to V bar by Cp 1 minus B by V bar minus 1. Okay, I'm just taking this negative sign inside so that, and then making this into V bar minus 1. Or we to subtract, take minus 1 outside and then multiply that, the minus sign is going to go. So we have this much. So now there are a few things we can do here. First and foremost, B is positive and it is B is positive, that means greater than 0, and B is less than 1, that we know, or most of the times B is much less than 1. Okay, so we can even further simplify it. Yeah, I'll do that, so for sake of simplicity. Okay, because we just want to know the sign. Okay, the exact value doesn't matter. Okay, somebody has joined in. All right, liquid sink. Can you hear me? Hello. Hello, can you hear me? Okay, please reply if you can hear me. So what I've been doing is I've been trying to solve some of the problems. Since no one was there, I was just solving everything on my own. I'm recording the meeting and I'll upload the video to YouTube. You can check whatever you missed till now. And maybe this question is almost over. You may not follow this, but you can always check in the YouTube channel. All right. But can you hear me? Can you confirm that? Okay, there's no reply. Fine. I'll continue the recording. Anyway, so you see the quantities over here. We have V bar, we have Cp, and since it's again a big quantity, this all these terms are going to be positive. Okay, V bar is V bar is greater than 0. Cp is of course greater than 0. V bar minus 1 is going to be greater than 0, of course, because it's a large volume. So because of that, what we're going to have here is, it's simple. Because of this, we have, so which basically means nu Jt is going to be positive. Okay, that is what we wanted to see. Nu Jt is going to be positive for a real gas or a van der Waals gas. So since this is positive, so what is also nu Jt? The Joule-Thomson's coefficient is also nu Jt is also equal to delta, okay, is delta T by delta P, constant enthalpy, right? So that is something that we know already, and that is greater than 0, which means that it's a positive slope. Okay, so what would happen is, which implies as pressure decreases, as happens in the Joule-Thomson's process, pressure decreases, the temperature also decreases. Temperature decreases. So basically the gas cools down. Temperature decreases. Oh, sorry. Temperature decreases, which means the gas cools down. Okay. The gas cools down. Cools down. Alright. So that was the question actually. So what would happen to real gas? We had to go through these derivations. What would happen to a gas that obeys van der Waals equation in Joule-Thomson's expansion? So as the gas expands, pressure is going to decrease. So as a result, temperature is going to decrease. The gas will cool down. Okay. So the statement is true. Yeah. So the statement is true. That's what we have calculated. Okay. So basically the statement was true. Statement is true. Okay. Yeah. So now let me go to my next questions. Yeah. Let me check if Lady Queen is still there. I don't think she's there. Okay. Fine. If nobody is there, let me just drink water. So then we can continue after that. Yeah. I hope you guys were able to follow it. It's been quite slow because I was also trying to go from the basics as much as possible. So now the fourth question is, what is the isothermal coefficient of compression for an ideal gas? So as you know, I think Sir covered this, told this formula in class, I guess, in the tutorial problems. Okay, so KT, isothermal coefficient of compression, is basically 1 minus V del V by del P at constant temperature. Yeah. So what we're dealing here is an ideal gas, all right? So since it's an ideal gas, as you all know, PV is equal to nRT. PV is equal to nRT. Okay, PV is equal to nRT, which means E is equal to nRT by P. So now we have to differentiate this del V by del P because that's what we have there. So KT is equal to minus 1 by V del V by del P. So what is that? So nRT are constant, so just take it out. nRT are constant. So P is in the denominator, so minus 1 by P squared. Great. Also, we can substitute this V as well. So that is going to be P by nRT into minus nRT by P squared. So that's quite straightforward. Now, this terms cancel, minus minus would cancel. So therefore, for an ideal gas, KT is equal to 1 by P. All right, 1 by P. So the dependence is basically P power minus 1. Okay, 1 is the, KT is equal to P power minus 1. That's it. F equal to P power minus 1. Yeah, so that's the fourth question. Now we'll go to the first question. Again, this is quite easy. I think a lot of you will know it already. So basically what we want to know is the enthalpy change when an ideal gas undergoes isothermal compression. So as we all know, H is equal to U plus P. Okay, so that we know. We can write delta H, which is the change in enthalpy, is equal to delta U plus delta PV, which can be written as delta nRT. So since this is an isothermal compression and the number of moles does not change and R is a universal constant, this term is going to be 0. Okay. And then since this is an isothermal compression, temperature is not going to change. This is also going to be 0. Therefore, enthalpy change is also going to be 0. So it's quite simple and straightforward. This is for compression or expansion, doesn't matter. It's going to be, the enthalpy change is going to be 0. All right. Yeah. Next is the exact differential problem. Okay. Yeah. So now we need to find out whether some of these functions that are given, total differentials that are given, are an exact differential or not, or an exact differential. So this is quite straightforward. Okay. So as you all know, given any function f of x comma y, it is an exact differential if exact differential okay, let me scroll down. Yeah, exact differential if it is, let's say, del f by del y x del x y is equal to del y del f by del x and y x. Okay, so this is the condition, but we do not have the exact form. We do not have that form over here. We have something different. Okay, so we have the total differential form where we have this. So del f by del y at x dy plus del f by del x constant y dx. So this is what we have over here in our problems. Okay, so that you can see. So let's say we'll keep this as m and we'll keep this as n. So it is an exact differential condition for exact differential. Exact differential f del m by, it was already differentiated by y, right? So x, when we keep y constant, is equal to del n by del y, keep x constant. Okay, it's as simple as that. So it's quite straightforward. Okay, yeah. So now we'll go through all the problems one by one. So what's the first function? Df is equal to, let me check, 3y square dx, 3y square dx plus dy what square, it is 6x squared. Okay, so 6x squared dy. So this is it. So now, since this one, what is that going to be? Dx, no? So that is going to be the n, and this is going to be the m. Alright. So now del m by del x constant y, what is that going to be? That's going to be, this is m, right? So if you differentiate it with x, with respect to x, it's going to be this. Yeah. So then del n by del y, and x is constant. There's no x, of course. It's going to be 6y. So they are not equal. Okay. Here del m, so del m by del x by y is not equal to del n by del y. So which implies it is not an exact differential, but an inexact differential. Okay. Yeah. So that's how we do the other problems as well. So let me check. First, I'll create some space. So we have second problem. Let me write down that. Df is equal to sine y, okay, sine y dx cos y is equal to sine y dx plus cos x dy, I guess. Yeah. Okay. Again, this is going to be easy. So this one is n. This is the m part. So the m del m by del x constant y is going to be this one, right? So that's minus sine x. So then del n by del y at constant x is going to be cos y, right? So again, they are not equal, not equal, not equal. So it is an inexact differential, which implies inexact differential. All right. So now let me create some more space and we can do the last problem. Till now we have had only inexact differentials, and I hope we get one exact differential. All right, let's see. Before that, I'll just see the problem and get it. Yeah, minus sine x dx y dy. Df is equal to minus sine x dx plus y dy. So now this is m, this is x, sorry, n. This is n. dm by dx is equal to, since it's y dy by dx, that's going to be 0. Similarly, dn is not a variable of y, n is not a variable of y, it's sine x, so again it's going to be 0. So therefore, they're equal. Dn by dy constant x, which implies they are exact differentials. Exact differentials. Yeah. Oh, wait. So I hope this is quite clear, because you just need to differentiate the variable with dx by y, and you have to differentiate the variable along with y by x, dy by x, and then they both should be equal for a given equation to be told that it's an exact differential. Okay, given function, sorry. Yeah. So now we come to the next question. I hope all whatever I've told till now is quite clear. If you have any doubts, you please post in the NPTEL forum. All right. So what we have now over here is we have to find the relation between temperature and volume in a reversible adiabatic process for a diatomic ideal gas. So this has to do with CPs and CVs. So first, in a reversible, I'll just keep adiabatic process. Reversible adiabatic process, as we know from class, the relation between temperature and volume is quite simple. So T2 by T1 is equal to V1 bar by V2 bar. Okay, it's not so clear, right? Yeah, V2 bar raised to the power gamma minus 1. Yeah, so that is quite straightforward. So that is quite straightforward. So now what we need is for a diatomic gas. Okay. So first let's check this case for monoatomic gas. So first let's see monoatomic gas. Atomic gas. Okay. In monatomic gas, what is CV? We can go from first principles, so like, I mean, from the basic actually. So as you know, CV is del U by del T at a constant volume, right? Okay. So that you guys are clear, I guess. So now what is U for an ideal gas? Again, see, this is an ideal gas. Okay, I have to check. I have to ideal, yeah. Because we are dealing with ideal gas in the question as well. So as you know, for an ideal gas, is RT or KBT, whatever you can put. Now, which implies CV when you differentiate at constant volume is going to be 3 by 2 R. Okay. So now, what is CP then? CP, as you know, is equal to CV plus R. So therefore, it is 5 by 2 R. So it's again quite simple. So now gamma, which is a ratio of CP by CV, is equal to 5 by 2 R divided by 3 by 2 R. 2 R divided by 3 by 2 R. This is going to be equal to 5 by 3. This is for monatomic gas. Okay. So the relation between temperature and pressure is going to be T2 by T1 is equal to V2 bar divided by V1 bar 5 by 3 minus 1. Okay. Sorry. gamma minus 1. So it is 5 by 3 minus 1. So this T2 by T1 is equal to V2 bar by V1 bar 2 by 3. Okay. Actually, this is quite simple. We can also write it the other way around. We can, if you want the bar to be somewhere over here, it's going to be 3 by 2 is equal to V2 bar by V1. So whichever way you prefer, we can do that. So this is for a monatomic gas, a monatomic ideal gas. What would happen if it's a diatomic gas? So that's the question. So we can again go from the start. So now P, it's a diatomic gas. See, in monatomic gas, since we can consider it like a particle, okay, simple particle. So what happens is it will have only translational degrees of freedom. So according to equipartition theorem, every degree of freedom for a given particle will have half kBT associated with it for the internal energy. Okay. So CBT, if you see U, since it's a diatomic gas, it will have, let's leave the vibrational degrees of freedom out of it. That's not required. We'll have 3 translational degrees of freedom, 3 translational and 2 rotational. 2 rotational degrees of freedom. So basically 5 degrees of freedom. So U is going to be 5 by 2 kBT or RT, whichever we can use that. So which implies CB, which is du by dt at constant volume, is going to be 5 by 2, 5 by 2 R. So then CP is going to be 7 by 2 R, right? Which implies gamma is going to be Cp by Cv, which is 7 by 5. Okay. So which implies gamma minus 1 is equal to 2 by 5. So now we can write the relation between temperature and volume for an adiabatic process for a diatomic ideal gas. Let me come down a little bit. Okay. Too much. Yeah. So this is going to be T2 by T1 is equal to, we have V2 bar, sorry, V1 bar, V1 bar by V2 bar. It's a gamma minus 1, so directly we'll substitute 2 by 5. So this is the final expression that we want. So this is the relation that we were after. All right. Yeah. So now we can go ahead and solve some numerical problems related to adiabatic expansion. So this relation might be useful in the future for calculating various work-related problems. So first we'll see some work-related problems for monatomic gas. So next two questions are concerned about that. Okay. So we are sticking with adiabatic process. So we are going to see expansion, adiabatic expansion, and we have an initial volume and a final volume, and then we have some initial temperature. We need the work done. So what is the work done in an adiabatic process? So for the adiabatic work and reversible, it's quite straightforward. We need CV T2 minus T1. Okay. So what are the things that we have? So CV, since it's an ideal monatomic gas, it's going to be 3 by 2 R. Okay, because it is ideal and it is monatomic. So that is the thing that we need. Monatomic gas. So now we have T1, which is equal to 300 Kelvin, but we do not have T2. However, we have V1 and V2 from which we can actually calculate the T2. Okay, so V2 is going to be equal to 16 decimeter cube. So since the number of moles is just 1, V1 bar is equal to V1 and V2 bar is equal to V2. So we don't have to worry about it. So we have the equation already, T2 by T1 is equal to V1 bar by V2 bar raised to the power gamma minus 1. Again, as we saw in the last problem, what is the gamma for a monatomic gas? It was 3 by 2. Okay, I think somebody joined. It's quite late, I guess. Somebody joined. Yeah. Hello, Rudra. Okay, I hope you're there. All right, Rudra. So what I've been doing is, since no one joined, I've been I've been solving the problems myself and recording the process, and I'll be uploading this video in YouTube. So whatever you have not seen till now, you can always check in the YouTube channel and post the questions in NPTEL forum. Now, if you want to continue in the class, you can actually follow along with me. So I've been uh, trying to find the work done for a reversible work going from one volume to another. All right. So, so now for monatomic ideal gas, gamma is equal to 3 by 5, right? So which means gamma minus 1 is going to be equal to 2 by 5. Sorry, did I do it wrongly? Yeah, 5 by 3, sorry. 5 by 3. Plus minus 1 is going to be equal to 2 by 3. Yeah, just give me a minute to plug in my power. All right. So now we already have this, so we can calculate. So T2 by T1 is equal to V1 bar by V2 bar, and that is 2 by 3. So we can see here we need T2, and T1 is 300 Kelvin, and V1 bar, what is V1 bar? V1 bar is 2 and V2 bar is 16. Since they are in the numerator and denominator, the units will cancel. 2 and 16 to the power 2 by 3, which is basically equal to 1 by 8, 2 by 3. So now T2 is equal to 300. And what is this? This is 1 by 2 and then 1 by 4. Yeah, 2, 1 by 4. So basically T2. So basically T2 is equal to 150. So I'll just keep it as 300 by 4 for now. 300 by 4 Kelvin. So we don't have to subtract things. So what we need is adiabatic work, reversible adiabatic work. CV is 3 by 2, 3 by 2 R. T2 is 300 by 4 by 4 and then minus 300. So this is going to be 3 by 2 R. This is what? This is 1200 minus, okay, it's 900 by 4. Okay, So I'll just get the calculator out. Just do that. Yeah, it's in scientific mode, yeah, of course. So what we need is 3 into 8.314 into 900 divided by 8. Huh? So basically, we have something minus 2000, 2000 point 97. So I'll just write it as 2006. Sorry, 2808, not 6 joules. So that is the adiabatic work done for a reversible expansion. So since it's an expansion, it's going to be negative, which makes sense. All right. So this is the problem over here. Yeah. Okay. Now the next problem is also on similar lines. So where we are going to calculate the work done for again a monatomic ideal gas, 1 mole of monatomic ideal gas at an initial temperature 300 Kelvin, again same. But then instead of volume, what we have now is pressure. All right. So we need to uh, get the relation between pressure and temperature for an adiabatic process. So we can easily, since it's an ideal gas, we can easily go from T2, the initial expression, T2 by V1, V1 by V2 bar. Yeah, be better. Gamma minus 1. So we can easily go from this to using this equation, using ideal gas equation. So which implies V1, V bar is equal to T by P. So which implies V1 bar by V2 bar, okay, is going to be equal to T1 by P1 into P2 by T2. Okay, sorry. Yeah. All right, somebody is here. All right, so Nisarg, I've been solving the problems already, and I'm recording this video, and I'll be uploading this in the YouTube channel. So you can follow all the problems over there. So probably you can continue. If you are continuing, I just have one more problem. I'm almost to the last problem. So basically, I'm trying to calculate the work done in an adiabatic, reversible adiabatic work for an expansion of a monatomic ideal gas. So since the common expression is between is relating temperature and volume, now since we don't have volume in the question, I'm converting the relation to a relation that will equate temperature and pressure. All right. So now we have T2 by T1 is equal to T1 by T2 gamma minus 1 gamma minus 1 P2 by P1 gamma minus 1. All right. Sorry. So now this is quite straightforward. T1 by T2 gamma raised to the power gamma P2 by P1 gamma minus 1. Okay. So we can even further reduce this. We can even further reduce this T2 by T1. And what I'm going to do is I'm going to raise it to the power 1 by gamma on both sides. So basically we have P2 by P1 gamma minus 1 by gamma. Alright. So what are the things that we have already? We have T1 is equal to 300 Kelvin. We have P2 and then we have P1. Let me check what is the value. What are the values? So it goes from pressure. P1 was initially 30 bar and then to a pressure of 5 bar. So 30 bar, 30 bar to a pressure of 5 bar. So since this is an ideal monatomic gas, gamma is 5 by 3 since it's an ideal monatomic gas. Okay, ideal monatomic gas. Yeah, it's quite straightforward. So now what is then gamma minus 1 is 2 by 3, which implies gamma minus 1 by gamma going to be equal to, what is this? 2 by 3 divided by 5 by 3, it's going to be equal to 2 by 5. So basically we have T2 by T1 is equal to P2 by B1 raised to the power 2 by 5. So now we have all the values. Let's substitute and then get T2 value. Okay, T2 is equal to 300. P2, what is P2? 5 by 30 to the power 5. So 5, then this is going to be 6. So take the calculator. So it's simple, right? 1 divided by 6 raised to the power, okay, let us raise. Yeah, raised to the power 2 by 5 is 0.4. Okay, into 300, right? Yeah. So basically we have T2 is equal to, what is that? 146 or something. Yeah, 146.5. 146.5. So the work done is going to be simple. So again, the work done, we have T2 now. Work done adiabatic reversible, which is equal to CV T2 minus T1. CV is T2 3 by 2 R. 146.5 minus 300. Which is, I'll just do subtraction here only, minus 300 into 3 by 2, which is 1.5, into R, which is 8.314. So basically the work done is minus 1914.2. Minus 1914.2 joules. This is WA reversible. Okay. Yeah. So it was quite straightforward. So if you have basically to calculate the work done adiabatic, we just need the CV of the system and T2 and T1. Let's say it's an ideal gas, we can easily get the CV, just do del U by del T at a constant volume because since I mean from equipartition theorem we can actually get the U as well, so it's quite straightforward to get the CV. So once we get the CV, we need the temperatures. So in most of the problems they'll give one temperature and ask you to find the other, and probably you'll have pressure or volume. So we just need to apply some of the relations and then get the other T2, and then it's just a straight algebra after that. All right. So now that's coming to the last question. Basically, this question actually has to do more with thermochemistry that will be covered in the next week, in week 4. But then there was one question. Okay, there was someone coming. Nobody. Yeah. But then there was one question that was asked. Okay. So there was one question that was asked in the assignment problem. So I've just designed a question so that you get a sense of how to deal with that problem. But it's again quite straightforward if you had gone through the subsequent week lectures. But I'll nonetheless I'll do it. So the relation over here is quite simple, okay? So we can get the reaction, I mean the relation between QP and QV using enthalpy and internal energy of a given reaction. So as you can see here, first we need to do is, of course, there's not going to be any work done on this system. This is just going to be related to the heat released in the reaction. Okay. So since work is not going to change, we will deal with it. So first, as you know, enthalpy is equal to U plus PV. So that is something that we know. So delta H is going to be equal to delta U plus P delta V or V delta P. So now first what we'll do is we'll consider U alone. U is equal to, as we know, Q plus W. All right. Or this is going to be equal to Q minus P delta V. So now at constant volume, volume, delta U is going to be, this term is going to be 0, right? So it's just going to be QV, constant volume. So that is one thing that we have. So now what we'll do is then we'll substitute this equation Q delta in the delta H equation. So Q minus P delta V plus P delta V plus V delta P. Okay. So now consider a constant pressure process. Constant pressure, if you consider a constant pressure process, this term is going to be equal to 0. So then delta H would become QP. Okay. So that was that. I mean, you can understand these two actually. So I'll do this, name this as 2 and this is 1. So if you consider reactions, they are a constant pressure and constant, most of the time it's a constant pressure process and constant temperature also. So if we'll consider the enthalpy, same enthalpy reaction, Q plus PV, then delta H is equal to delta U plus delta PV. So now in this question, we are considering the reactants and products as ideal. So then we can use the ideal gas equation. So PV is equal to nRT. Okay. So then this would become delta U plus delta nRT. So as you know, temperature is going to be constant. R is universal gas constant. So delta N is going to change in the reactions, right? So because of that, delta H is equal to delta U plus delta nRT. But then this we know is QP from 1 and 2. I'll just write from 1 and 2. This is going to be QP, and delta U is going to be QB plus delta N RT. So delta N is the number of moles gained in a reaction, or difference over there. Okay. So we have our equation over here, which is basically just hydrolysis. Just, sorry, we can call it hydrolysis. Just have some equation over here. So between reactants, the number of reactants, okay, delta N. So basically, we need to find the delta N of this reaction. Okay. So if you see delta N is equal to number of moles of products minus number of moles of reactants, which is in this equation is equal to 1. So it's a straightforward answer after that. You just need to come. So the relation is going to be equal to QP is equal to QV plus 1. So it's going to be RT. So this is the final equation. So which option is it? It's the D option. So like this you can do for various reactions. I mean, if there are some reactions, we can always do for that. All right. So that's the end of the discussion for today. And I will stop presenting. Yeah, so that's the end of the discussion in today's TA session. So what you can do is you can go through the video or you can solve the assignment problems. If you're able to solve all the assignment problems, then well and good. If you can't, and if you still don't understand after seeing the video, you can always put an NPTEL chat box and forum, I mean, and then we'll be there to help you with it. All right. So thanks for watching the video.